So, homework number 9 on chapters 10 and 11 was due on the 3rd. That's Wednesday this week. We're going to finish up chapter 13 today. We'll have a review of chapters 10, 11, and 13 on the 8th. That's Monday next week, and the exam on chapters 10, 11, and 13 on the 10th. On Wednesday this week, or if we have time at the end of the day, probably Wednesday this week because there's so few people here, I'll cover some of chapter 12 because I wanted to talk about gravity, but it's not going to be on the test. If you have any labs you need to make up, you can do it on Wednesday at the lab time, or Monday and Wednesday next week from around 10 to 2 p.m. or on Wednesday this week from around 10 to 2 p.m. You can come in and do a lab. Any questions? So let's finish off chapter 13. So, when you have oscillatory motion, there's conservation of energy. So in an ideal system with no conservative forces, the total mechanical energy is conserved. So kinetic energy plus potential energy, 1/2 mv squared plus 1/2 kx squared, and that equals a constant. And since we know position and velocity as functions of time, we can find the maximum kinetic and potential energies. The maximum potential energy is 1/2 Ka squared. The maximum kinetic energy is 1/2 ma squared omega squared. Omega squared is K over m, because omega is square root of K over m. So that is also 1/2 Ka squared. So the total energy is 1/2 Ka squared. So as a function of time, it's 1/2 Ka squared cosine squared omega t plus 1/2 Ka squared sine squared omega t. So 1/2 Ka squared says times cosine squared omega t plus sine squared omega t, or 1/2 Ka squared. So the total energy is constant. Energy just trades back and forth between kinetic and potential. As the kinetic energy decreases, the potential energy increases, and vice versa. A similar thing happens with a pendulum. Potential, kinetic potential, and back and forth. So this shows how the energy transfers from potential to kinetic and back. And the sum is the same at all times. Because 1 plus sine squared plus cosine squared always equals 1. So a pendulum, a simple pendulum of mass m, of negligible size, suspended by a string or a rod of length L and negligible mass. So, you have some small mass on some string of length L that has negligible mass, like this. And it turns out the angle it makes with the vertical varies with time as a sine or a cosine. For small angles, it approximates simple harmonic motion. The bigger the angle gets, the worse the approximation is. So if we look at the forces on a pendulum bob, we'll see that the restoring force, the force pushing the pendulum back towards the center, is proportional to the sine of the angle. So there's tension, mg, because we have mg sine theta, pushing back towards the center. And that's the transfer, that's the force creating torque. Whereas the restoring force for a spring is proportional to displacement, which would be theta in this case, because we're talking about how the angle is changing. But it turns out for small angles, sine theta and theta are about the same. So if your pendulum is not making really big swings, you can easily describe it as a harmonic oscillator. And if we substitute theta for sine theta, this allows us to treat the pendulum as in a mathematically identical way to a mass on a spring. And we find the period of the pendulum depends only on the length of the string. So torque equals moment of inertia times alpha, which equals tangential force times radius. Airframe, right? Just making sure I'm not screwing anything up. So what we get, moment of inertia times alpha is mass times length squared times alpha equals minus mg sine theta times length. One of the lengths cancel, and we get length times alpha equals minus g sine theta. So, and if we replace sine theta with theta for small angles, we get length times alpha equals minus g theta. So the period ends up being 2 pi over the square root of m over k, which is m over mg over L, basically. And you get the period of a pendulum is 2 pi times the square root of the length of the pendulum over g. The mass of the bob actually fully cancels out. So the period of a pendulum depends only on the length of the pendulum arm. This is what, or, this is the idea behind how we, like a grandfather clock. It uses a long pendulum arm that swings once every 2 seconds as a timing device. Now, a physical pendulum doesn't quite match this. It's a solid mass that oscillates around its center of mass, but it can't really be modeled as a point mass suspended by a massless spring. So here are some examples. A disc on a string. The length is this, the center of mass is here. We have a bar, we have a bone. These are all physical pendulums. We approximate the ideal pendulum in like a grandfather clock by having a big mass on a relatively thin rod to swing back and forth. But it still boils down to moment of inertia times alpha equals, you get moment of inertia divided by mass times length equals g theta. So with a bit of calculation, you just get the period depends on the moment of inertia. It's moment of inertia over mass times length squared. The square root of that. That's the sort of modifier. But for a mass on a string, moment of inertia is mass times length squared. So they cancel, and we'll get back to 2 pi square root of L over G. So the pendulum in a grandfather clock is designed to take 1 second to swing in each direction. So the period for a pendulum is 2 pi square root of L over G, as opposed to period for a mass on a spring, which is 2 pi square root of K over M. No, it's not. So the pendulum in a grandfather clock is designed to take 1 second to swing in each direction. That is 2 seconds for a complete period. On the length of a pendulum that has a period of 2 seconds. So we know our period is 2 seconds. We know G is 9.8 meters per second squared. We know our length. The length is what we want to find. So we know period equals 2 pi length over G. So period squared equals 4 pi squared length over G. So length equals G T squared over 4 pi squared. So 9.8 meters per second squared times 2 seconds squared over 4 pi squared gives us 0.994 meters. Just a touch under a meter in length. And if you need to adjust the pendulum on a grandfather clock, your clock is running too slow, you raise the pendulum up, you shorten the length to make it run faster. If it's running too fast, you lower the pendulum down. You lengthen the length to make it run slower. So if you look carefully at a grandfather clock, you'll notice the weight at the bottom of the pendulum can be moved up or down by turning a small screw. Suppose you have a grandfather clock at home that runs slow. Should you turn the adjusting screw so as to raise the weight or lower the weight? And when a clock runs slow, it means it takes longer than it should to complete one cycle. So period is 2 pi L over length over G. The main thing you want, the only thing you can adjust is L. G is a constant, 2 pi is a constant. You want to make periods smaller, so you will make the length smaller, so you will raise the weight. You need to reduce T, so you should reduce L, so you should raise the weight. Now, sometimes, actually very commonly, oscillations don't continue forever. There's not only that restoring force of oscillations, but there's some non-conservative force of drag, which will tend to decrease the amplitude of the oscillation and is typically proportional to the speed. So typically it's proportional to velocity. So this causes the amplitude to decrease exponentially with time. So the amplitude is, A naught. If you just have this equation, the solution looks like amplitude equals A naught, original amplitude, that's e to the minus bt over 2m. If you include the oscillation, you get something that looks like x equals A naught times e to the minus bt over 2m times cosine omega t, where omega is, the natural oscillation. I think there's a phase term in there. It's been a while since I actually solved that differential equation, but it's not. It's basically the oscillation you would have, but it's damped. It reduces. It looks something like this. So you would have this oscillation normally, but it shrinks according to this equation, e to the minus bt over 2m. There's an exponential decay in the amplitude. So this is the case that's known as underdamped. You can't have a high enough damping. So this shows a case where it's underdamped, where the dominant motion is still the oscillation. The damping slows it down, but it still allows it to oscillate. You can have a situation where the damping is strong enough that it never actually oscillates. That's called overdamped. So the dominant motion is actually the decay from the damping. So the previous image shows a system that was underdamped, goes through multiple oscillations before coming to rest. A critically damped system is one that relaxes back to equilibrium position without oscillating, and in minimum time, it's perfectly balanced between oscillation and damping. And an overdamped system is one that won't oscillate, but it's damped so heavily that it takes longer to reach equilibrium. Basically, it heads towards equilibrium, but the whole time that damping force is fighting against the return force. So that's a damped oscillation. Most real oscillators are damped. So, you know, if I have pendulum on a string and I start it, you'll notice the amplitude steadily decreases, because there is various frictional forces that are roughly proportional to velocity. And that was underdamped. You know, things like shock absorbers are often attempted to be critically damped or maybe overdamped, because you don't want your car to go wobble, wobble, wobble whenever you go over a bump. Now, an oscillation can also be driven. So if I have a weight on a string, if it's not driven, but I can drive it, I can cause it to oscillate. And I'm not driving it at the right frequency to get maximum oscillation. But so if you have some oscillating driving force, the frequency of the driving force may or may not be the same as the natural frequency of the system. So damping reduces the amplitude of motion, but if you drive it, that will add to the amplitude of motion. And in that case, when you have a driven oscillation, if the driving frequency is equal to the natural frequency of the system, that will lead to the maximum amplitude. It will absorb the most energy. So if the driving frequency is close to the natural frequency, the amplitude can become quite large, especially if the damping is small, and this is called resonance. If you've ever seen that trick where a singer shatters a wine glass by singing at it, that is inducing a resonance in the wine glass with the sound they're making, so that the wine glass gets a very high amplitude of vibration and breaks. So you want to drive the wine glass with sound at its natural frequency. Lots of things use resonance. Things resonating at their natural frequency is also why when you like pluck a guitar string, you get a particular note, because it strengthens. When you pluck a string, you send a whole bunch of different frequencies in, but you get the damping affects frequencies out of resonance much more than frequencies in resonance. So here, if I take this jar and I whack it, now this doesn't work very well. Let me get a beaker. Beakers have better sound. So if I have this beaker, if I hit the beaker, I put a whole bunch of different frequencies in it. It's basically random. But it has a resonance frequency that will naturally ring out at. Oh. So that was. And that's how things like bells and such work. So we use resonance in musical instruments all the time. That is the end of the chapter. So the period is the time required for a motion to go through a complete cycle. Frequency is the number of oscillations per unit time. Angular frequency is 2 pi times the frequency, or 2 pi over the period. Simple harmonic motion occurs when the restoring force is proportional to the displacement from equilibrium. The amplitude is the maximum displacement from equilibrium. Position is a function of time. Looks something like x equals a cosine 2 pi over period times t, or a cosine omega t. And velocity as a function of time is minus a omega sine omega t. And acceleration is minus a omega squared cosine omega t. The acceleration is minus a omega squared cosine omega t. And that's how you can find omega for a mass on a spring, for example. Omega ends up equaling k over m, because omega squared, because this is minus omega squared times x, and acceleration is minus k over m times x. Just a little bit of algebra gets you that. The period of a mass on a spring is 2 pi square root of m over k. Omega is square root of k over m. The total energy in simple harmonic motion is 1/2 Ka squared, where A is the amplitude and K is the spring constant. Potential energy as a function of time is 1/2 Ka squared cosine squared omega t. Kinetic energy as a function of time is 1/2 Ka squared sine squared omega t. And a simple pendulum with small amplitude exhibits simple harmonic motion, because small angles approximate to the sine of the angle. The period of a simple pendulum is 2 pi L over G, where L is the length and G is just G. And the period of a physical pendulum, it's not just a mass on a weightless rod, is 2 pi length over G, where length is the length of the center of mass, and G is G times moment of inertia over mass times length to the center of mass squared. There's an adjustment factor for the moment of inertia. Oscillations, when there is a non-conservative force, are called damped. If it's underdamped, the amplitude will decrease exponentially with time, where A naught equals minus bt over 2m. Critically damped, there's no oscillation. The system relaxes back to equilibrium in minimum time. And overdamped, there's also no oscillations, but it's slower than critical damping. And an oscillating system can be driven by an external force, and this force may replace energy lost to friction, or it may cause the amplitude to increase greatly at resonance. And resonance occurs when the driving frequency is equal to the natural frequency of the system. Any questions? 33. Guess I could do a little bit of chapter 12, but probably just gonna. I will at least give you the most important equation from chapter 12. So that's the end of what's going to be on the test. Stop sharing. Share again. Fix that bug. So chapter 12 is about gravity. So we've been dealing with gravity near the surface of the Earth, where we just approximate it as a constant times mass. But the more general version of gravity is that gravity is a force between two objects, any two objects. The Newton had the insight that the force accelerating an apple downward is the same force that keeps the moon in its orbit. So universal gravitation. So the force of gravity is a force between any two objects that have mass. That force is proportional to a constant, big G, times the masses of the two objects divided by the distance between those two objects squared. It's called an inverse square law. Electricity is very similar to gravity. Electricity also has an inverse square law. So the radius is the distance between the masses. G is a constant referred to as the universal gravitational constant. And its value is 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. The gravitational force is always attractive. It always points along the line connecting two masses, and the two forces shown are an action-reaction pair. Big G is a very small number. This means the force of gravity is negligible unless there's a very large mass involved, such as the Earth. So we notice gravity from the Earth because Earth is really big, and so the mass of the Earth causes a gravitational attraction on everything that's significant. But the gravitational attraction between just like things in the room is negligible. Gravity is by far the weakest of the four fundamental forces. The four fundamental forces are gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. And from weakest to strongest, they go gravity, which is very weak, then weak nuclear force, then electromagnetism, then strong nuclear force. Pretty much all the forces you encounter on a day-to-day basis, other than gravity, are electromagnetic force. Variations on it. The weak nuclear force and the strong nuclear force only act at very, very short distances, like inside an atom distances. So G is a very small number. This means the force of gravity is negligible. If an object is being acted on by several different gravitational forces, the net force on it is a vector sum of the individual forces. This is called the principle of superposition. So as an example, if you have two apples of mass 0.11 kilograms and mass 2.22 kilograms sitting on a dining room table, and you want to find the force of gravity when their separation is 13.2 centimeters and 132 centimeters, G is 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. Mass 1 is 0.111 kilogram, mass 2 is 0.22 kilogram. For the first case, radius is 1.132 meters. For the second case, it's 1.32 meters. We want to find the force. The force is big G times mass 1 times mass 2 over radius 2. So 6.67 times 10 to the minus 11 Newton meters squared over kilogram squared times 0.11 kilograms times 0.22 kilograms over 0.132 meters squared. This force is 9.26 times 10 to the minus 11 newtons. Consider that the weight of the smaller apple is about 1 newton. So this force is tiny. You wouldn't notice it at all. And if they were a meter, 1.32 meters apart, this would be 9.26 times 10 to the minus 13 newtons. Because we increase the distance by a factor of 10, that decreases the force by a factor of 100. That, I think, is all I'm going to cover for today, because there's very few of you here. I will continue on with chapter 12 on Wednesday.